I guess now the recording has been started. All right, welcome to another ACM seminar. So today we are very happy to have Dr. Guannan Zhang from Oak Ridge National Laboratory. For briefly, Dr. Zhang is currently a senior research staff in machine learning and data analytics group at Oak Ridge National Lab. And he received his PhD in applied mathematics at the Florida State University in 2012 under guidance of well-known mathematician Max Gunzerberg. And then he joined the Oak Ridge in 2012 as the Householder Fellow. And recently, he received the DOE Early Career Award in 2022. And he has been holding a joint faculty appointment with the Department of Mathematics and Statistics at Urban University since 2014. So today, he will going to present a non-local gradient for high-dimensional black box optimization in scientific applications. Please, Gunnar, stage here.
Yeah, thanks for the invitation. Very happy to share my recent work with my collaborators at Oak Ridge on a non-local gradient for high-dimensional black box optimization with some applications in science and engineering. So this is, I'd like to acknowledge my sponsor, the U.S. Department of Energy, and the Oscar and Math Program, and the AI Initiative at Oak Ridge National Lab. So let's see. Yeah, so here is the outline. First, I will introduce the background of black box optimization, and then I will introduce our main method called the non-local gradient using a directional Gaussian smoothing. We have proposed a method and algorithm, and also I want to show some numerical tests on benchmark functions, and we also have some theoretical analysis on the convergence of the non-local gradient descent for strongly convex functions and also for a class of non-convex functions. And the next section is about the adaptive non-local gradient descent. Basically, the non-local gradient we define has several sensitive hyperparameters. And in order to not, the performance of the non-local gradient depends on the hyperparameters. In order to save the time tuning the hyperparameters, we kind of develop adaptive algorithm that can automatically adjust all these hyperparameters along the way together with the optimization. So, and after that, I'm going to introduce some of the applications that we have applied this non-local gradient methods to, especially some science problems that are related to DOE's application. So, okay. Now, black box optimization means if it's very simple that I want to optimize or minimize loss function f of x in the high-dimensional space. Here is the d-dimensional space, and black box scenario meaning we only can evaluate the loss function. We either don't have access to the local gradient of the loss function f of x, or the local gradient is not very useful. For example, when the loss function is highly non-smooth and noisy. And those black box optimization algorithm has a lot of applications. Some of the examples includes, for example, when the optimization problems involves a legacy code like PD solver that you cannot obtain the gradient of the loss function because old PD solvers is not automatically differentiable. And also another application is the optimization of neural network architectures, basically hyperparameter tuning, which can be viewed as a optimization, black box optimization problem. And reinforcement learning is another one because of the underlying dynamical system. The simulation usually is also not differentiable, automatically differentiable. Okay, so here is a brief overview of the black box optimization papers. There are two very good overview papers if you're interested. And basically, this is an incomplete list of extensive literatures. For example, I categorize them into the following classes. And the random search is the first one, we are all very familiar with Nesterov's methods, Bandit methods, those purely based on random search. Simplex method, those are like very famous and well established. You can almost download those softwares from any Python libraries like SciPy or NumPy, like Nelder-Mead methods, and also surrogate methods, surrogate models, meaning like instead of optimize the original loss function directly, we first build a surrogate model to the loss function either globally or locally, and then we optimize the surrogate model. And the methods including interpolation methods or trust region methods. So Bayesian optimization, another popular one recently for black box optimization. The reason why it's popular because it involves some kind of uncertainty, so that and also it handles the it does not have a structure at all. So basically, it's very flexible to use. But the downside of Bayesian optimization is that it cannot handle a very high dimensional problems. Also, paralyze the evaluation of the functions, loss functions in the context of Bayesian optimization. So evolutionary algorithm, like called the covariance matrix adaptation evolution strategy, or other smoothing-based techniques like the sixth one, also, I mean, they all belong to this evolutionary algorithm. And our method belongs to the class of smoothing techniques, basically, because the original loss function may not have a good local gradient, but we provide some smoothing to the original loss function so that the smooth function has a much better property. Okay, so here is the Gaussian smoothing based random search. This is, I mean, the baseline that we build upon to develop our methods. So basically, Gaussian smoothing means if the original loss function f of x is not differentiable, and we can, or it's very noisy, then we can define a smoothed loss function f sigma by doing a Gaussian convolution. Basically, you convolve the original loss with the Gaussian kernel. And then the smoothed function can be represented by a expectation with respect to a d-dimensional Gaussian distribution. So then, under this representation, even if the original loss function is not differentiable, the smoothed function is always differentiable. So in fact, the gradient of the smoothed function can also be represented as a high-dimensional expectation of just the loss function itself plus the increment. So we want to emphasize that. So this evaluation of the gradient of the loss function, of the smoothed function, does not involve the gradient of the original function, which makes it easy to use. So with this formulation, there are multiple ways to approximate the gradient of the smoothed function. For example, you can just use random sampling or Monte Carlo sample to approximate the expectation, the high-dimensional expectation. And the simplest way is just a random search. You just pick one sample at each iteration in your gradient descent and use that sample to determine this, to approximate this expectation. And then you just use gradient descent to find the next, to update the state. If you can use one sample, then you can use multiple samples. And here is a
quick question here.
Yeah, sure.
What does the sigma represent here?
Oh, sigma represents the smoothing radius. Basically, we
that controls the variance.
Yeah, it controls the radius. Basically, we pulled it out of the Gaussian kernel. It was supposed to be in the Gaussian kernel, but we just want to do some normalization. We just pulled it out. So you can view it as the smoothing radius. You know, gotcha. When sigma equals to or goes to 0, it converges to the local gradient of f if exists, right? When sigma is very big, if sigma is very big, then the smooth function will converge to a constant function eventually. Right.
Yeah, thank you.
So that controls the smoothing radius, basically how smooth you want. Sigma is a very important parameter especially you will see in the analysis. So now, if you can use one sample, you can use multiple samples, then which means you can use Monte Carlo estimator to approximate this Gaussian, this high dimensional expectation. And there are multiple ways, a lot of work to, improve Monte Carlo samples by, doing orthogonal sampling or using the history to build a subspace that you only sample within the subspace, something, so on and so forth. There are multiple versions of it, but there is a significant challenge in this type of techniques lies in especially for high dimensional problems, because of the low accuracy of the Monte Carlo estimator or random estimator of the high dimensional integral, right? If you look at it, the gradient of the loss of the smooth loss function involves a d-dimensional integral for every partial derivative. So if you have d dimensions, you have d partial derivatives, and each of the partial derivatives has a Monte Carlo error, and all those errors will accumulate such that the estimated gradient direction is totally wrong from the exact gradient, so which cause a very slow convergence if you use this smoothing technique to solve high dimensional optimization problem. And there are, in practice, because of that, people handle this in two ways. First is, as you can see, when you use a very small sigma, the smoothing region is very small, then the accuracy is not very sensitive to the number of samples, Monte Carlo samples you use. That turns out the most common setting that people use the Gaussian smoothing technique. But when the sigma is very small, you cannot handle multi-modal loss functions, because you are just approximating the local gradient of the loss function. So when you want to handle some non-convex loss functions with a lot of local minimum, you want to use a bigger sigma to smooth out this local minimum. But when you use this big sigma, you suffer from the low accuracy of the Monte Carlo sample. So basically, you are in this kind of dilemma. So that motivated us to develop our non-local gradient in order to avoid the use of the Monte Carlo estimator. So to do that, we developed this called the new Gaussian smoothing involves only very low dimensional. Actually, it's just a 1D integrals. And because it's a 1D integral, we can really perform non-local exploration to define a non-local gradient that can avoid a lot of local minimum in optimizing multimodal functions. And because it's only 1D integrals, we can use much better or accurate numerical integration schemes to estimate the non-local gradient. Okay, so here is the main idea is called the directional Gaussian smoothing. Basically, the key idea is instead of smooth out in the isotropically in d-dimensional space, we only conduct 1D long-range explorations or smoothing along d orthogonal directions in the RD space. Each of this long-range exploration defines a non-local directional derivative as a 1D integral. And because of that, because it's only 1D integral with respect to Gaussian kernel, so we can use Gaussian-Hermite rule, quadrature rule, to estimate these 1D integrals to avoid the low accuracy of Monte Carlo sampling. Now, here is the details. So first, we define to perform a 1D smoothing, we first define a 1D function, which is the cross-section of the original loss function along the direction like defined by Cassie. That's the direction. And this g of y is just a 1D cross-section. And we only perform, for given Cassie, we only perform 1D smoothing, Gaussian smoothing along Cassie to define this g sigma, which is the 1D smooth function. And with that, we can take a derivative of g sigma to get the directional derivative of the smooth function along the direction c. And that this defines a partial or directional derivative non-local. And you can see we also have a sigma here, but this sigma can be much bigger because we only involves 1D integral along that specific direction c defined by c. Okay. And now, in order to define a gradient operator, we need D partial derivatives. So we can choose a orthogonal system, in the RD space defined by c1 through cd, and along each direction we define this directional. We perform 1D smoothing, and then we take the derivative so that to formulate a directional derivative along each of the D directions. And once we have all those, we can stack them all together to define our called the non-local gradient. We also call it the DGS gradient because we use the directional Gaussian smoothing to define this gradient. And of course, this gradient depends on the smoothing radius sigma and also the orthogonal system. For local gradient, usually the local gradient does not depend on the choice of the coordinate system. But the non-local gradient, since we perform non-local exploration, it does depend on the choice of the orthogonal system, which turns out to be a very important hyperparameter that we need to choose. I'll talk about it later. So, okay. Now here is the illustration on how the DGS gradient works. We use the 2D non-convex function as the loss function. The contour represent the shape, the geometry of the loss function. And we assume we are right now the current state at the center of the loss of the domain. And the global optimum is indicated by the black star. And if we compute the local gradient, you can see on top and on the right are the 1D cross sections along the two directions. The blue curve represent the original 1D cross section, and the red curve represent the smoothed cross section. So if we compute the local gradient, which is the blue arrow, you can see it points to a totally wrong direction because of the fluctuation of the 1D cross sections. Well, after we perform the smoothing, and the red arrow is the DGS gradient direction, which is our gradient direction. And you can see because of the smooth cross section, the red arrow points to a much better position. If we perform the gradient descent along the red, the direction indicated by the red arrow, that will be much better performance. So that illustrates like how this DGS gradient works. Okay, and this plot also illustrates the influence of the smoothing radius on the non-local gradient. Here is also 2D highly non-convex, our benchmark function. We use that. We view it as the loss function, and the red arrow also represents the DGS gradient, which is the non-local gradient direction, and the blue arrow represents the local gradient. You can see on the left, we have the smoothing radius to be 0.01, which is very small. And in that setting, you can see most of the blue and the red arrows align with each other, agree with each other, which means in this setting, our non-local DGS gradient is try to approximate the local gradient, which is not what we want to use for non-local or non-convex optimization. And on the right, the sigma equals to 1.0, which is big relatively. So in that setting, you can see all the red arrows point to the center of the domain, kind of, which is the location of the global minimizer. And the blue arrows, which represent the local gradient, that points to wrong directions. So this is also illustrate how this non-local gradient works for non-convex optimization problems.
Can I quickly ask one follow-up question here?
Sure.
Okay, it's very interesting. Have you tried the much larger sigma in this exact same case? So I'm just curious that whether how the direction would change if you have a much larger sigma in this case.
Well, if it's too big, basically the reason why it works is because this loss function has kind of like a global convex structure and perturbed by some local, not local, but perturbed by some smaller scale or higher frequency noise or perturbations. So the smoothing is really to smooth out the local fluctuation and capture the global structure. That is why it can capture this, can find this global minimizer. So the smoothing in the analysis will show. So basically, the smoothing radius, the best smoothing radius, is the one that is comparable to the wavelength of the perturbation.
That makes sense.
Right.
All right. Thank you so much.
Yeah. So that's basically what it is. So, okay. Now, this is we know. Okay, this non-local gradient works fine, and then we need to find a way to approximate it. Like what I said, instead of because it only involves 1D integrals, we can use Gaussian quadrature rules to approximate each of the partial derivatives, and which give us a much better convergence rate than the Monte Carlo based estimator, which is exactly one important reason why we want to do the directional smoothing. Okay, and after that we can just stack all the Gaussian-Hermite estimators together to formulate the estimator of the DGS gradient, and then we put them in the context of gradient descent and perform just a gradient optimization. So, okay, this very simple algorithm to summarize. So basically now I want to show you some benchmark test problems. So we tested several benchmark functions that people commonly use for global optimization. We choose 6 of them for the first set of tests. And the first two called sphere, which is nothing more than a quadratic function. The first two are convex functions. The first one is the isotropic quadratic function, which is we have to test. It's benchmark. And the sharp range means even though it's convex, but it has some ill conditioning. Basically, it varies much faster along one direction and slower along the other direction. So it has some ill conditioning. If you compute the Hessian matrix of this loss function, the Hessian matrices have some ill conditioning issue. So, and the third, fourth, and fifth one are the most interesting one because they are highly non-convex. The Ackley, Rastridge, and the Schreifer, those are the very famous functions that people develop to test to benchmark global optimization algorithms. So the way those functions are defined, like what I said, is it has somehow a convex base and then perturbed by all kind of periodical noises. That's the way that how these functions are defined. If I mean, you can find the definition online. So, and the last one is the one that has no global structure and also very non-convex. We choose this function to show that even our method does not work, cannot find the global minimizer of this function. So to show, I mean, basically for global optimization, no method can handle all the functions. Okay, here is the comparison of our method for 2000 dimensional in 2000 dimensional space. So we can see for the sphere and the sharp range, and we compare with several existing methods. And for example, the Nesterov, also the finite difference. We use finite difference to approximate the local gradient. You can view the finite difference as a local gradient descent. And we also compare with some of the evolutionary algorithm called the CMA-ES. The IPOP CMA is a state-of-the-art version of the CMA-ES methods. And also the Monte Carlo-based gradient estimator, we call it ASEBO. with dimension reduction using active subspace. And you can see for those comparisons, for convex problems, yeah, I mean, our method works, but there are also other methods also works fine, especially finite difference. It also can quickly find the global minimizer for convex problems. And the advantage of our method really stand out is on this highly non-convex functions like Ackley, Rastrigan, and Schleifer. None of the other methods can find a global minimizer, but our method, because we can kind of smooth out the local fluctuation caused by the noises, and then we can find the global minimizer. And for the sixth one, none of those methods works. So it's just an illustration. And then we do some scalability test to see if we keep pushing up the dimensionality, what's going to happen for our method. And turns out that even though the number of function evaluations required by our method keep increasing with the dimension, as you can see, there's no surprise here because we do directional smoothing. So basically the cost or the number of function evaluations will grow linearly with the dimension. And we can see here, even though it grows, but we can all find for Ackley, Rastrigan, and Schleifer, we can all find the global minimizer still, even though the number of function, the cost is higher. But for the other method, in 2000D, they cannot even find it. I mean, there's no point, there's no way they can find the global minimizer in higher dimensional space. So that really illustrates the advantage of our method.
Can I ask two questions in the research? Very interesting. And you mentioned about the use of the quadrature. I wonder how many quadrature rule do you use on the test?
Well, for the test, we use like, most of the time we use 7, we use 7, less than 10, basically. Less than 10.
Then does it mean that with respect to the number of the quadrature point being used, you have to increase the function evaluation because the...
Yeah, sure.
I see.
Sure. But if you, I mean, in practice, yes. I mean, that's not, people sometimes worry about it, right? But in theory, so for those functions, they're all very smooth. It's just a fluctuate, right? They have infinite number of orders of derivatives. So from that perspective, the quadrature rule converge pretty fast, much faster than Monte Carlo.
Right. I see.
In high dimensional space, especially when we use a bigger smoothing radius.
Right. And my second question is that, and also you use some orthogonal systems for choose the direction.
Yeah.
I wonder, you just fixed one for all, or you generate the new direction of every iteration?
Here we just fixed, for those tests, we fixed one for everything because it's kind of isotropic, and even the sharp ridge has some ill conditioning. It's not too bad. But later we'll show like how to adjust the coordinate system. It needs to be adjusted, especially for like ill conditional problems.
I see. That makes sense. One minor follow-up question is that the number of the direction you can choose actually does not need to fill up the entire space. Is that correct? So that I think one of the slides shows that you have the matrix transpose, so that, which means that you don't really need to have a full dimension to run this algorithm. Is that correct? Yeah, here.
Yes. The transform, this one is necessary because you need to count, because those partial derivatives defined under the coordinate system of C, right? You need to transfer it back to the canonical coordinate system so that you can perform gradient descent, because X are defined in the canonical coordinate system.
Right.
You have to transform it back to the, but like you are right. So we are thinking about like, if there is a low dimensional structure that we can capture. So dimension reduction is one thing that we are thinking about, which for many, I mean, for a lot of functions, it will work, but as a general optimization method, we don't want to kind of, because when you perform dimension reduction, you're kind of trying to lean more towards the exploitation rather than exploration, right? If you lean too much towards exploitation, you might get stuck in some local minimum. There needs to be some, you may lose some robustness of your algorithm, right? So it's just a trade-off, I think. So if you develop a code for general users, you want your code to be robust.
Yeah, sure.
You probably need to sacrifice some performance, right?
Yes.
But if you use it by yourself, then and your function evaluation is very, very expensive, then you will try your best to cut down the function evaluation. That just depends, I think.
Yeah. Thank you.
Yeah. So so some theoretical results. So first, we want to do some sanity check about our non-local gradient, in the sense that we see, okay, what happens if we use our non-local gradient to approximate the local gradient of the loss function? What will happen? This is kind of the sanity check. So basically we can see if we estimate this difference, and the error is bounded by two terms, and the first term is caused by the Gaussian-Hermite quadrature rule, and the second term is caused by the smoothing. And for both terms, you can see there's a sigma, which is a smoothing radius here. And when sigma goes to 0, the error will go to 0, which demonstrates like, for the smoothing radius goes to 0, our gradient will approximate the local gradient. That's kind of the first sanity check. And here we consider a very highly the strongly convex function. So here is the comparison with other methods in approximate gradient. For example, if we want to approximate the local gradient with the error maximally to be epsilon, so what the smoothing radius should be and how many samples we need. For our method, to achieve the accuracy epsilon, the smoothing radius sigma needs to be like this, epsilon over 4L. L is the Lipschitz constant, or square root of dimension. And we need this many samples. And we can see, we compare with the finite difference, with the Gaussian smoothing, with sphere smoothing. So we can see our method is not the best, in terms of approximating local gradient. So that's why, I mean, this is a sanity check. If you want to approximate local gradient, you probably should just go with the finite difference or local Gaussian smoothing. Okay, now the analysis of basically the error bound of if we use gradient descent using our non-local gradient to optimize a strongly convex function. What is the error? Here we can see the error is bounded by the x star is the global minimizer. So the error is basically caused by our algorithm is delta sigma, which is this form. You can see again, when sigma goes to 0, the error will go to 0. And when the sigma goes to 0 and the iteration number goes to infinity, the error will go to 0. So which is a good sanity check for our methods in optimizing strongly convex functions. And here is the comparison of if we want to see if we want the loss to be within the epsilon ball, around the minimum loss function values. So our method requires this number of samples versus the random search Gaussian smoothing requires much smaller number of samples, but the number of iterations we required by our method is much smaller. So which means even though our method asks for more samples or function evaluations, but all the function evaluations within each iteration can be parallelized. So if you have a bigger computer, then our method is really efficient. Okay, and now we comes to the analysis of the non-convex objective functions. Like what I mentioned before, so our method is really good at optimizing a convex function perturbed by some noise. So this is what we're going to analyze. So basically, the loss, if we assume the loss function is the sum of a strongly convex function plus a random noise, not a random noise, just a noise, okay? And what we want to find is the global minimizer of the convex function. Then see if our method can do it or not. And we consider two scenarios of the noise functions. The first one is we assume the noise is a periodic. And the second one is we assume the noise is band limited. Basically, band limited means if you expand the noise using Fourier series, you have a lower bound on the frequency. You know, when we, in terms of optimization, higher frequency noise usually is easier to deal with. And what will cause problems is the low frequency noise or perturbation. So now we first talk about this, periodic, when the noise or perturbation is a periodic function. So we can see if we use the gradient descent, this is the error bound, X star is the global minimizer. And the optimization error is also represented by the delta sigma. And we can see compared to the strongly convex function, here we have an extra term. And alpha is the frequency of the perturbation or the noise, eta. So here we can see we cannot, in order to reduce this delta sigma, the error, we cannot just reduce sigma, the smoothing radius. So because alpha is, when alpha is small, when alpha is big, then we can use small smoothing radius, no problem. But what causes trouble is when alpha is small, basically when we have a lower frequency perturbations. At the beginning, we need to use a big sigma of smoothing radius to make sure this whole term is under control. So that is the reason that justifies why we need a big smoothing radius for non-convex functions. Okay. And here is another one on the, so the band limited function noise is just a generalization of the periodic noise. Basically, it could be non-periodic, but we have very similar result. Here, alpha is the lower bound of the frequency. And we can see the error term is determined really by the slowest frequency, the mode, right? Frequency, the alpha. And we need to, at the beginning, we need to use a very big smoothing radius to balance, to make sure this term is small. The third term is small. And of course, once you get into the mode that contains the global minimizer, you need to shrink sigma so that you can converge to the global minimizer. And here are some examples about how to choose, depends on the lower bound of the frequency, how to choose the best sigma to achieve the good error, to balance those errors. Okay, so now with this analysis, we finished this the second part on the classical, the directional Gaussian smoothing, and our algorithm has some hyperparameters in there. So we want to basically remove those hyperparameters, tuning of the hyperparameters, and try to come up with some adaptive algorithm. So there are like 4 important hyperparameters: the choice of the coordinate system, the number of Gaussian quadrature rule points, and the smoothing radius and the learning rate. So we're going to talk about each of the 4 hyperparameters, see how to adjust them automatically. So first is the coordinate system. I mean, the easiest way, the reason why we need to change the coordinate system is to handle the yield conditioning problem. And the easiest way to handle yield conditioning problem is to introduce the second order information. So, and the second order information, the most famous algorithm is the BFGS. to exploit the second order information. So in here, it's natural for us to first test how to integrate DGS gradient into BFGS, which is very, very simple because we just replace the local gradient in BFGS algorithm with our DGS gradient. And the rest form the same. So this is natural, and it works fine for some problems, but here it does not change the coordinate system in the BFGS. Now we have another way to exploit the second order information. Basically, we borrow the strategy in this called the covariance matrix adaptation CMA method. We borrow that to help us find the best to adjust the local coordinate system. So if you're not familiar with that, I mean, here is just a general procedure algorithm. If you're not familiar with that, I have some good illustration to show how to use this covariance matrix algorithm to adjust the coordinate system that we define the DGS gradient. So basically, it uses gradually updated covariance matrix. Let's see, on the very left, the contour represent a highly ill-conditioned loss function, ellipsoidal or loss function. And if the current state is right here, so we want to determine which two direction. This is a 2D case. We want to determine which two direction we should do the 1D exploration. The canonical direction is, of course, along the original coordinate system, which is not very efficient because none of those. The best direction is along the diagonal, as we can see. So the way that CMA works is at each stage, it draw a bunch of samples. Start with the isotropic or standard Gaussian distribution. Once you draw those samples, you can evaluate the loss function at all those samples, and then you can rank those samples by the loss values. And you only pick like the top, for example, 50% of the good samples, and you use that 50% of good samples to compute a sample covariance matrix. And then the sample covariance matrix will be used to draw more Gaussian samples. For example, if you do the iteratively multiple times, your Gaussian samples will concentrate more in the high probability in the contour region like this. Here I performed 5 iterations here. If I keep performing that, you can see the Gaussian samples will gradually concentrate within this ellipsoid. And the covariance matrix is like this. So now if we perform some eigendecomposition of the covariance matrix, we can find those eigendirections. And those eigendirections are the direction we perform 1D exploration to define our non-local gradient. And also those eigendirections defines this coordinate system. So, and we can combine this strategy with our non-local gradient descent, to adapt it and adjust the coordinate system along the way. It's very useful for highly ill-conditioned problems. It seems like a waste to have more samples to update the covariance matrix, but compared to the waste in the when we solve ill-conditioned problems, this cost is neglectable, I would say. Yeah, and also we can use this strategy to help us cut down the dimensions. For example, if we can see the dimension, there are 2 eigendirections here. One is with the bigger eigenvalue, the other with the smaller eigenvalue. And the one with the smaller eigenvalue is actually the one with a bigger with a bigger gradient. But because it has a smaller eigenvalue, we can just cut it down. We don't need to evaluate any Gaussian quadrature along those directions. We only perform 1D exploration along the directions with the big eigenvalues. So we can use the eigenvalue essentially to perform dimension reduction, also to cut down the number of Gaussian quadrature points that is needed. And in terms of the learning rate, here we use a very naive line search strategy, because we perform a non-local exploration, and we think this non-local gradient is point to a much better direction, so we should explore further along that direction. That's why we have this backtracking line search strategy. We changed the standard backtracking line search slightly by introducing a non-local regime. Instead of having one shrinking factor, we have two shrinking factors. The non-local shrinking factor is bigger than the local factor, basically shrinks slower, so give us more time to explore the non-local region. And we also need to have a local, to explore the local region very well to make the algorithm more robust, because after we escape from all the local minimum, once we are approaching the global minimizer, we need to reduce the smoothing radius, and we need to explore the local region to get the final convergence. In that scenario, we do need to explore the local region. That's why for robustness, we include both the local and non-local backtracking. And the smoothing radius can be also adjusted by looking at the average displacement the state moves for past history, like in a short history window. The intuitively it's very easy. So when the state only moves around, the displacement is very small, then which indicate that we may need to shrink the smoothing radius because we are probably approaching a global minimizer. We start with a big smoothing radius, but as the state does not move very much, so we need to gradually shrink it. Of course, in practice, we also need to use some restart strategies. Once we see the smoothing radius goes to very small and the state does not change, then we need to probably restart re-enlarge the smoothing radius and do it again, see if it comes back to the same state, same optimizer. So, but this strategy seems performs very well for our testing problems. Yeah, and with all this we put together, so we have this adaptive algorithm that essentially we don't need to tune any sensitive hyperparameters anymore. Now we test this adaptive algorithm with more benchmark functions. Here we have 12 of them. Some of them included in the primary test, but we also include more, especially those highly ill-conditioned functions. We test them in the 1,000 dimensional cases, and some highly ill-conditioned functions, including this Rosenberg function, an ellipsoidal function. And as we can see, our method can find the global minimizer very fast. All the minimal function, loss function values are 0. And it does not affect the performance of our method in optimizing these multi-modal functions like Ackley or Rastrigan, Schreifer, Quintic. Those are the typical like multi-modal functions. And the wavy function is the one that we prove again, like no method will work because it does not have a low dimensional structure to exploit. Here is another scalability test for all the functions for our method. We pushed from 2000D to 6000D. Again, the number of function evaluations increases with the dimension, but we can all find the global minimizer pretty good. So now I don't know how much time I have. Okay, pretty much. So I'm gonna briefly go through some of the examples that we have. We applied our methods to. So we have applied to our method to topology optimization, to reinforcement learning, to some additive manufacturing problem. Basically, it's more like more on the side of model calibration. So here is the topology optimization. Basically, we want to design this kind of a bridge architecture, and the way we design it is that we treat each pixel as an independent design variable. So it's not a parametric model. And then the design constraint is that we only allow 20% of volume constraint. Basically, only 20% of the pixels can be black. And we want to maximize the load bearing of this structure. And there are a total number of 2,400 design variables. And we can see our method performs pretty good compared to all the other baselines. And this is the final design. You can see the final design, our method has a lot of big structures, and versus as opposed to the other baseline method, they find some local minimum because their structures are much smaller, which is hard to build. So this is kind of the illustration on a high-dimensional topology optimization problem. And here is the problem that we apply to is the additive manufacturing problem. Like basically for additive manufacturing, people want to build computational models to simulate the laser path when you're printing like metals, for example. And the high fidelity finite element simulation is very expensive. So people develop called the semi-analytical simulator, which is fast but less accurate. So we use our method to help them to tune the parameters or estimate the parameters of their semi-analytical model so that their model accuracy is comparable to the finite element methods. And here's another one, is a very important problem at the spallation neutron source at Oak Ridge. The spallation neutron source is a unique, scientific imaging techniques compared to X-rays. Instead of using X-ray, we use neutron to do the imaging of some material to study the material structure. But the neutron as a heavy particle is much harder to generate. So Oak Ridge has the only one neutron source in US. In the spallation neutron source, there's one important component is the neutron target. Basically, it's where the neutrons are generated, and the target has a lifetime. So we use our method to help them predict the lifetime of the neutron target so that they have a better understanding of when we should prepare for the change of the target in order to avoid the disruption of the facility operation. So it's also an inverse problem, and I go through it fast. So basically here, those are the curves that people measured at the instrument, and after calibration, the calibrated model can produce the very similar curves as the measurement data, which means our method really did a decent job for solving this problem. Okay, I think that's all I have. And so in conclusion, so we developed this directional Gaussian smoothing technique. That the main idea is to avoid approximating high-dimensional integrals. Instead, we use a bunch of low 1D integrals, so which we can use Gaussian quadrature rules to approximate. And this strategy enables us to do long-range exploration to avoid local minimum in optimizing our multimodal functions. So there are some limitations, right? So basically, our method works only for functions with a global structure. If the function does not have a global structure, our method cannot find the global minimum. And some future directions, I mean, the non-local gradient is a very general concept. We can apply it to many other, in many other contexts, like that requires gradient, basically, like the Hamiltonian Monte Carlo, etc. So yeah, that's it. Thank you very much.
All right, thank you so much, Guannan. What a wonderful talk. Are there any questions from the audience? Let me ask one question.
Yeah.
So actually, I was working on similar project that somehow trying to not use the gradient information directly, and somehow I followed the fractional gradient theme. But with something came up is that, all right, initially, and also you mentioned in the introduction that suppose that we don't really have a gradient information, so the only oracle we have is a function value, right? Then hypothetical, then if that is the case, then the method being developed should work for the cases where the gradient doesn't exist in principle. So it got me to think that principle, so that, all right, then why don't we try to optimize something that the gradient doesn't exist? So that I tried with some function, like let's say some step function. And we know that from the real analysis, based on the step function, we can approximate any function. That's the Lebesgue integration approach. So that I was trying to approximate a function using step size, step function basis, and try to run it. And obviously we know that the gradient doesn't exist because gradient being zero.
Yeah.
Then actually all of a sudden it doesn't work. So, and then you may also see that, but the theoretical analysis, we have to always align closely with the gradient information, somehow following the classical convex analysis. So can you a little bit comment on that, what you might have in that some discrepancy? You know what I'm saying? So initial idea was that, all right, let's try to optimize something that the gradient may not exist. But at the end of the day, the functions, the examples or analysis, all are somehow relying on the fact that the underlying objective has a gradient.
Yeah. So I think we look at it two ways. The first is, even the gradient exists, but the local gradient is not very helpful for the multimodal. Like if you have a non-convex loss function has a lot of local minimum, the local gradient even exists, but it's not going to be very helpful. So that's one scenario. And I think our method mainly, especially the analysis or everything, mainly attack that scenario. I agree with you when the gradient does not exist at all, especially for the discontinuous functions.
Right.
It depends. It depends. If you say if I use a piecewise constant function to approximate like a quadratic function, I think this smoothing technique will, as long, I mean, depends on the how accurate your piecewise constant approximation, right? If each piece is very small, it's very accurate, each step is very accurate, then it's very small, then the smoothing will work, I think, because it will smooth out this discontinuity, right? If you use that, if the piecewise constant function is approximation of a convex function or something like that, or some global structure, I think this algorithm will work. And the local gradient will definitely not work, because the local gradient will be zero or infinity, right? So for piecewise constant, but this algorithm will work. But if you're talking about a very bigger pieces, I think if you talk about piecewise constant function, then the width of each piece kind of similar to the concept that in our analysis, the wavelength of the period or the wavelength of the local fluctuation, something like the smoothing radius need to be bigger than the width of each piecewise constant and each piece, so that it can capture the global structure, right? I think something like that.
I see. That makes sense.
Yeah.
Thank you. Are there any other questions?
I had a question, Dr. Zhang. So
Yeah,
on
sure.
your slide 31, you showed that computing the covariance matrix. So, but for very high dimensional problem, will it not be cumbersome to compute the covariance matrix?
That's right. For very high dimensional problems, it's going to be costly because, I mean, the eigendecomposition, it will be costly, but it depends. So basically, the eigendecomposition, if you treat each covariance matrix as an independent covariance matrix, then it's a cubic complexity. But if you treat it as so when we do this called the exponential smoothing, you know, when you each time you only update, do a low rank update, then you can reduce the complexity to near quadratic. So which is much better. But I agree. I mean, in general, this kind of you know, covariance matrix adaptation does not work very well for very high dimension. That's also the reason why the CMA algorithm is not designed for very high dimensional optimization. It works very well. The CMA algorithm works very well for low D problems, but when it goes to high D, it starts become very slow, and also, you know, in high D, these Monte Carlo samples cannot capture. I mean, sometimes cannot capture the structure, but you know, this feature is usually needed when we approximate highly ill-conditioned problems.
Yes.
If you have a highly ill-conditioned problem, which is also very high dimensional, then it's like the neural network training problem, right? You're gonna see battle all the time. You're never gonna reach the global minimizer. Yeah.
And also just a follow-up question on the Ackley function. So just working on one of the projects with Dr. Shin. So we just realized that the initial point for the minimizing the Ackley function is also like sometimes very sensitive for finding the optimal optimal of the function. Did you observe that thing in your method also? Like, how do you initialize?
Yeah, depends on the dimension. So Ackley function is a type of function that has a very flat outer region, and a very sharp minimizer, local mode. And in 2D, you can say, okay, it should be okay in 2D. In high D, the mode that contains the global minimizer, the volume of the is much smaller compared to the outer region. So it's very hard. I mean, in high D, your initial location will be around a corner for sure in high dimensional space. So it doesn't, in high D, it doesn't matter, because if you do random sampling, like it's almost probability 1 that you're gonna start from some corner, which is bad enough. In low D, yes, that's right. So basically in our test, all we do is in like 2000 dimension, we randomly pick uniformly sample the initial condition in the unit box, in the box. So not in the L2 sphere. If in the L2 sphere, you can really control that, right? The distance between the initial state and the mode that contains the global minimizer. We didn't take advantage of that. I mean, basically what we did is at the beginning it's always a lonesome corner, and we just start from one of the vertices of the hyperbox, you know.
Thank you. Very excellent talk. I really enjoyed it. So
thanks.
All right. Then that's it for today's ACM seminar. Let's thanks again to Dr. Zhang for a wonderful talk. Thank you very much.
Thank you.